Yeah, so this time I'm going to be talking about models with latent random variables. So this is kind of a more advanced topic. As we get closer to the end of the class, we're covering some more advanced things. And I think it's an interesting topic because it exposes us to a different variety of unsupervised learning than we've been handling before. Like up until now, we've done a lot of unsupervised learning of representations, but now this allows us to do unsupervised learning of like latent structure or other things like this. So I think we should spend at least one class on it. Cool. So going back to the very beginning of the class, when I talked about discriminative versus generative models, most of the models we've handled in this class are discriminative models where we calculate the probability of an output y given an input x. Generative models can calculate the probability of a variable x or multiple variables x and y. So we either just have the probability over x, or we can define multiple variables here. And just as a little bit of practice, which of the following models are a discriminative model versus a generative model? So let's say we have a BiLSTM part of speech tagger or a BERT part of speech tagger. What kind of model is that? Any ideas? Yeah. Yeah, the part of speech tagger is discriminative. And just for completeness, what is X and what is Y? Yeah, X is the word and Y is the part of speech, or you could say X is the sequence of words that you take as your input, and Y is the sequence of the parts of speech that you take that you're generating as your output. But yes, yeah, that's correct. We actually didn't talk about CRFs that much, so I can skip that. But if we think about a language model, what about a language model? Yeah, it's basically a generative model because you're calculating the probability of your input. You can also, in a way, think of it as kind of a discriminative model, where you take in your input up until this point and generate the output. So particularly when you use, generate the continuation of the input. And so when you use a language model as a, model to do prompting or something like that, it almost like turns from a originally generative model over the input text that you have into a discriminative model where you're trying to predict an output given an input. But basically, language models are predicting the probability of a sequence X, so we can treat them as a generative model. So another thing to talk about is types of variables that we want to handle. And we can think of observed variables versus latent variables. So an observed variable is something that we can see from our data. So this could be language model text, or if we have a corpus consisting of text and annotated parts of speech, then those annotated parts of speech would also be an observed variable because somebody has given them to us as observable data. A latent variable is a variable that we assume exists, but we aren't given the value of it. And then we also have deterministic versus random variables. So a deterministic variable is essentially a variable that can be calculated directly from the input according to some deterministic function. Whereas a random or a stochastic variable is variables that obey a probability distribution and may take any of several or infinite values. And so here are some definitions here. And then if we take a quiz, what type of variables are these? So in an attentional sequence model using maximum likelihood estimation or teacher forcing, Are the following variables observed or latent and deterministic or random? So like, let's say we have the input word IDs. I wrote F here, but it could be X also. Yes? Observed and, yeah, essentially deterministic because, you know, they're given to us. There's only one possible value. We're also not calculating a probability distribution over them at all. What about the encoder hidden states? Yeah. Latent and deterministic. Yes, this is important. So a lot of people, you know, might not think of these as, you know, deterministic variables. They might think that they're kind of probabilistic or unknown, but we have a single function that calculates them. We never calculate the probability over the hidden states. So they're deterministic variables. What about the attention values? This is a trick question. Or it's not a trick question, but it's a tricky question. Any ideas? Observed or latent is probably easy, right? Yeah. Yes, it's latent and deterministic, and that's why it's kind of a little bit tricky, right? Because attention values look like probabilities, but they're not actually probabilities, right? We're just normalizing them between 0 and 1. So these are also deterministic values. And the output word IDs, what about these ones? Any ideas? Yeah, they're probabilistic, so we could treat them as random variables. And what about observed or latent? What's that? Yeah, observed, or another way you could think of them is observed at training time, but not observed at test time. So, but they're observed at training time, so you would normally call them observed variables, I guess, and then you might want to infer them later. So this is, you know, what we know so far. And if we talk about latent variable models, a latent variable model is a model that induces a probability distribution over variables. And usually when we talk about a latent variable model, we're talking about the X variables are observed at learning time in a data set, and Z are latent variables. But all of these variables are random variables. And there's also other varieties of latent variable models where you have like deterministic variables that are observed at training time. Like you could also have a conditional latent variable model where you have your observed input, your observed output, and then a latent random variable here, Z. But most of the ones I'm going to talk about today are basically like this, where they induce a joint probability distribution over the observed input X and a latent random variable Z. And I'll give some examples. So what types of latent variables can we be inducing? We can be inducing latent continuous vectors. And these would be things like a standard variational autoencoder, which I'm going to be talking about soon. There's also latent discrete vectors. So there was a very brief mention of topic models a few classes ago. Topic models are latent variable models that induce discrete vectors. And then there's also latent structure. So we can have hidden Markov models or latent tree structured models. And for example, depends syntax induction, like what Hao talked about earlier, is an example of something with a latent tree structured model. So the most common way to do induction of any variety of latent variable in a neural network model nowadays is using something called a variational autoencoder. Variational autoencoders are a pretty broad set of models, but there's a very typical, like stereotypical instantiation of them using latent continuous vectors, and that's what I'm going to be talking about first today. So in the latent variable model, using latent continuous vectors with variational autoencoders, we often set things up a little bit like this. So we have an observed output X. We could assume that this is a continuous vector for now, but this could also be text or any other variety of variable we want to estimate the probability of. And then we have a latent variable Z, where this latent variable Z is generated by a Gaussian. And then we have a function F parameterized by theta that maps from Z to X, where this function is normally a neural network. And that's parameterized by the theta. So here's an example. I'd like to point out that in the reading, I have this tutorial by Gorsh. And this is a very nice tutorial. It's explained in very clear terms and things like this. So if you want to go back and review, I suggest taking a look at this. But basically, for Z, we have this these points that are sampled from a zero mean unit variance Gaussian. And we take these points and we learn a mapping function to the latent space that we want to be modeling here. And sorry, to the observed space that we want to be modeling here. So this latent space Z gets mapped to the observed space X. And this observed space X can be arbitrarily complicated. Obviously, what I'm showing on the figure here is not Gaussian, right? It's a circle of some variety, so it's not a Gaussian. But this could also be the space of all images in the world. So it could be the space of like all multidimensional images. It could be the space of text. So X could be any arbitrary space we want, even if Z is still a Gaussian. Yes, I see a question. Uh-huh. So if you have a model where given the same input always gives you the same output, why would that not be deterministic? So if I rephrase, let's say you have a machine translation model where the machine translation model, you put in a sentence, you always get the same sentence as output. Why is that not a deterministic model, basically? So that's a really good question. In that case, the only reason why you get the same output is because you're doing something like a beam search or argmax search. So you're searching for the output that has the highest probability, and kind of by definition, that's a deterministic function. But normally when we train the model to estimate the probability of the output. So if instead we sampled from that model, we would be able to get a distribution. We'd be able to get different samples according to a probability distribution. So basically, there's no way to sample hidden states, right? Because we don't ever induce a probability distribution over hidden states. But there is a way to sample the output word IDs because we have a probability of the output and we sample them. Attention is also a little bit tricky. You could theoretically sample, an attention value if you wanted to. Because it's a probability distribution, so you could sample over it, but we never do that, or we never really intended to do that when we trained the attention model. There are varieties of attention models that have like discrete attention, but that's not how we use them, I guess. So. Mm-hmm. Yeah, the latent variables are random variables. The the outputs here are actually deterministic given the inputs, but because they are dependent on a probabilistic variable, they themselves also are considered random variables. Yeah, very good question. So, any others before I move on? Okay, so just to reiterate, the thing on the left is almost always, in this particular variety of model, is almost always a Gaussian distribution, simple Gaussian distribution that can have an arbitrary number of dimensions. The thing on the right can be any distribution. And the reason why this works is because the thing on the left, this is a distribution over continuous vectors. And as long as we have a neural network in the middle here, neural networks, as we talked about before, are universal function approximators. They can approximate any function under some light conditions. And because of this, despite the fact that this is a really simple function, a Gaussian here, you can map that onto an arbitrary complicated function. So you can generate, big pictures or sentences or whatever else from a variational autoencoder. So if we think about this from a probabilistic perspective, basically what we do is we draw latent variables from the prior, and we draw a data point from the probability of x given z. And this results in a joint, this can result in a joint probability distribution over the data and latent variables. A deterministic function is a probability distribution with a single point on the output. So because the essentially if we turn this into a deterministic function, this would still induce a probability distribution over x. Maybe that also follows up on the previous question, because it would just be that this p of x given z would be 1 for a single point. Okay, so how do we calculate a loss function here? We would like to maximize the log likelihood over the entire data set that we have. This is our standard function that we optimize when we're training any of the models that we train nowadays. And for a single example, the likelihood of this example is the marginal likelihood here. So basically the probability of x given z and the probability of z, and then we integrate over all of the possible z's here. And that, kind of by the definition of what integration looks like, this is going to be true. However, we can't, because basically this distribution here, or this value here, is parameterized by a neural network and is extremely complicated. There's no way we can exactly solve this integration. So what we do instead is we sample values from this probability of z, and then we sum together to get the final values. So looks like this basically. We calculate a set of hidden variables sampled from z, and then we calculate the probability of x like this. So because z is a simple distribution like a Gaussian, it's well known the best way to sample from an exact way to sample from a Gaussian. This is easy to calculate. Yeah. Mm-hmm. Mm-hmm. Yeah, so I haven't talked about the encoder yet. You actually don't need an encoder to train this model. The reason why you don't need an encoder to train this model is because you could just sample this and maximize this value, right? However, there's a big problem with doing that in terms of efficiency. And because of that, there is also an encoder, which I haven't talked about yet, but I will. So here we have two tasks of interest. The first task is to learn the parameters theta of this P of X given Z. However, another thing that we might want to do is, given a particular X, we would like to know the latent variables that would give you a high probability of X, essentially. So, or that have a high probability here. And the way we can calculate this is using Bayes' rule. Bayes' rule, I think a lot of people might have seen it in a machine learning class, but basically it's a way that you can take a conditional probability in one direction and reverse the order of it and multiply by some of these values here. And so here we have P of X given Z. So this is our decoder. We have P of Z, which is our prior. And then we have P of X, which is the marginal probability over all of the Z's. But as we mentioned before, calculating this is intractable. So we aren't able to calculate this directly. So we were talking about sampling-based approximations and things like this. So because this is intractable, we would like to have a more efficient way of being able to predict, being able to basically calculate the probability of Z given X here. And variational inference approximates the posterior with a family of distributions parameterized by by phi here. And so essentially what we do is we learn another model to calculate the probability of the C given X. So we have one model to calculate the probability, of X given Z, and another model to calculate the probability of Z given X. And this is called an inference network, usually in variational autoencoders. So a reason why you would want to do this, actually, is another reason why you want to do this goes back to the bias and variance trade-off that we talked about before. So we talked last class about how if you sample randomly from a distribution where there's a big variance in the values, you're not going to get a very good estimate of the values in some cases where you draw bad samples. And in this particular example here, let's say we randomly picked values from here, each of which maps approximately to some point on this circle. And we selected 3 values and they all happen to be down here and map into this part of the space. Our estimate of the probability of this point would be really bad, right? It would be really low because we're selecting values from parts of the space that give a very low probability to this point up here. However, if we happen to sample like this point or a point near this point, we would get a high probability. So basically, if we just sample things randomly from the prior probability here, it's not going to give us a very good estimate of, it's often not going to give us a very good estimate of the true probability of X, the true marginal probability of X. So because of this, also, if we want to try to calculate this probability here, we would rather like to have a way to efficiently infer the latent variable Z that give us a good estimate or give us a high probability of X as well. So that's another function of the inference network. Okay, so I'm going to go into some details and then maybe you can take some questions after this. But basically, what we do to infer, to approximate this true posterior over the hidden latent variables with this inference network here is we try to minimize the KL divergence between the inference network posterior and the true posterior here. And there's something called the variational lower bound, which is often called elbow for like evidence lower bound. And basically this, the log probability of X is equal to the evidence lower bound plus the KL divergence between these two values here. And the way we calculate the evidence lower bound is basically by having the expected probability between the expected probability of the generator of the generative probability of the values you've seen given the latent variables, where you sample the latent variables according to the inference network. And then you additionally have a term that calculates the KL divergence between the inference network's estimate of the latent variable here and the prior probability of the latent variable. And basically what this implies is by optimizing this evidence lower bound, we will be indirectly optimizing. We'll be optimizing the lower bound over the true log probability that we want to be optimizing. So I'm not going to go through like all the math here. It's in the tutorial that I linked on the site if you want to go through it kind of in more depth than this, but hopefully this gives you the general idea of what the math looks like. Yeah, so in order to minimize this, you want to be maximizing the evidence lower bound. So another way you can look at this is essentially, let me also show on this figure here. So basically what you do procedurally when you train the model using this latent variable model is you have two models. You have one model that calculates the probability of the output of the observed variable X given the latent variable Z. So that was our P theta of X given Z. And then we have our other model. The inference network that predicts Z given X. So when we get a new point in this space here, we infer the latent variable Z, and then we reconstruct X given this latent variable Z. And so this is another reason why it's called a variational autoencoder, because we have this encoder or inference network, which predicts Z, and then the decoder, which predicts X given Z. And that also helps solve the problem that I talked about here. So the problem here is essentially that if we sampled a whole bunch of things from Z and they all gave a low probability for X, then we wouldn't ever get a good estimate of X, of the marginal probability of X here, because all of the probabilities would be low. But here, given that the inference network is attempting to predict places in the space where we have an X that gives a high probability of Z, that lowers the variance, essentially. It lowers the chance that we're not going to get a good Z whatsoever. And so because of that, that allows us to do more efficient learning. So we don't have to draw a million samples in order to get one sample that gives a high probability of X. We only have to draw, one sample or 5 samples or something. So that's what it looks like here. We have this reconstruction loss, and we have the KL regularizer over here. And the so we take X, we do inference, and we predict Z, and then we take Z and we calculate the probability of X. So another way you can think about this is we can think of it as a regularized autoencoder. So a regular autoencoder, what it would do is it would just be like an encoder. Encoder and a decoder. Where the encoder and the decoder predict a hidden variable here, and then calculate the probability of X given this hidden variable. But here we have the additional regularization here of the KL divergence between the predicted probability of Z and the prior probability of Z. And what this does basically is this prevents the model from predicting just any point in the space, and actually encourages it to predict points in the space that more closely match the prior probability here. So more closely match this Gaussian probability here. And so why is this important? This is important because let's say we want to use this as a model. Well, it's important mathematically for this model to be, correct in the first place, to be a correct joint probability over Z and X. But it's also important if you think about wanting to generate from this model. So in this case, we can generate by randomly sampling a point from a Gaussian distribution and then mapping it onto X. And that would give us, some point on this circle in the simple case here. But also if we train the model on images or something like that, it would generate random images because we would sample a point and then it would convert it into something that looked like an image, or we would sample a point and it would convert it into some text if we trained it on text. However, if we just use an autoencoder here, there's no distribution over H. H is just a deterministic variable. And so because of that, there's no way we could actually sample from H in a principled way. And the model wouldn't be basically wouldn't be working as a good generative model. Okay, so I think that's a basic idea. Oh yeah, so if we remove the prior, yeah, there we go. Yeah, so if we remove the prior, we wouldn't know what what this would look like here, and so we wouldn't be able to generate them in a regular autoencoder. Okay, are there any questions about what I talked about so far? Yeah. So the Z here is a vector. So the Z would be like one point in the space here. The exact way we parameterize the inference network and use it to induce a distribution Q of Z given X, I think I'm going to be talking about in a slide or two. But yeah, Z is basically one of the vectors in this space. Any questions? Okay. So how do we learn the VAE? So the VAE looks a little bit like this. And one way that we could learn the VAE would be to use this inference network to sample a variable from Z. So the way we form the inference network, is that we have X, we have an encoder, and then given the encoder, we predict a mean and a covariance matrix that induces a probability distribution over the over the latent variable. So basically, the probability distribution over the latent variable becomes the mean as induced by the inference network and the covariance induced by the inference network. And remember, we had two parts. We had the KL regularizer, and we had the probability distribution. So here, because we're talking about a simple probability distribution over continuous vectors, we can use something like the mean squared error loss, which tells us the probability according to a Gaussian distribution over the output. So we can replace this by our language modeling loss or any other sort of probabilistic loss that we want for a generative model. But basically, this is just the log probability of the output. Here is our KL regularizer that we talked about before. So our KL regularizer here. So now we can see we have a computation graph with two loss functions. However, the probability is that if we sample Z from the normal distribution here and feed it into the decoder, the loss from this thing here is not going to be able to backprop into the encoder, because sampling is basically an operation that breaks backpropagation. It's choosing a single discrete point, and there's no gradients that can flow through it. So one way we could solve this, not a good way, but one way we could solve this is by using reinforcement learning or any of the structured prediction algorithms that we talked about in last class. So we use sampling, we calculate the reinforce objective, we add a baseline or something like this, and we learn this encoder network. That would work, at least in theory, but it would add a huge amount of variance into the process because, you know, when we sample something bad, it wouldn't give us a good signal. So one of the reasons why VAEs became so popular is because they have something called the reparameterization trick, which prevents this sampling from breaking backpropagation. And this is really, really clever. And it spawned a whole new set of similar methods for different applications. So basically, what they observed is that they need to be sampling from a Gaussian distribution with a mean and a covariance matrix. But there's a special property of the Gaussian distribution, which is any Gaussian distribution, if you want to sample from it, you can first sample from a zero mean unit covariance, zero mean identity covariance Gaussian distribution, then multiply it by the covariance matrix and add the mean, and you get the other Gaussian distribution. You get the Gaussian distribution, the original Gaussian distribution that you want to sample from. And so once you do this, you can realize that now there's a full path of backpropagation all the way back into the encoder. So because you moved the sampling operation earlier, this is no longer non-differentiable, and you can just calculate without any like reinforce or other tricks like this. So this is kind of the secret behind why variational autoencoders are so easy to use compared to many other things. Any question about this? Yeah. So is this the reason why people use the Gaussian distribution for the prior? There's two reasons. So that's one. The other reason is that the KL divergence between two Gaussian distributions is very easy to calculate. So you can calculate this in closed form. So it's like you don't need to do any tricky things here. Any other things? Okay, great. So now I'd like to look at an example. We can generate sentences with variational autoencoders. So when we talk about generating from language models, if you remember, we can use ancestral sampling. We can generate from a normal language model. So basically, while we have not reached the end of the sentence symbol, we could we generate the next word and we get an output. We can also generate conditioned on something. So we could do, translation or image captioning where we generate the output based on the input, like this. But there's a paper generating sentences from a continuous space by Sam Bullman. And basically, the way this works is we have a VAE-based approach, which is a conditional language model, but it's conditioned on the latent variable Z. So instead of conditioning like a translation model on the input, we condition based on this latent variable. So this is a little bit like an encoder-decoder model, but the latent representation is a latent variable and the input and output are identical. So basically, it's like the encoder-decoder without attention, because the encoder-decoder with attention, we're directly attending to the input representations. The decoder-encoder without attention, if you remember all the way back to the beginning of class, basically we generated a single vector and passed that on to the output. So that's also what we do here. So it's like this. We have the sentence X, we have our inference RNN to infer a latent variable, and then we have a sentence X. So why would we want to use latent variables? This could potentially allow for a more consistent latent space over sentences. And one motivating example from this particular paper is if you take a standard encoder-decoder model and you take a standard autoencoder model, you take, I went to the store to buy some groceries and horses are my favorite animal. And you take the hidden vectors for both of them and you gradually move in a line between the hidden vector for this sentence and this sentence. We get something in the middle, like I store to buy some groceries, I were to buy any groceries, horses are to buy any groceries. So it's kind of like strange sentences that wouldn't appear in real life. But for the VAE, we do a similar thing, and it's like, I want to talk to you. And then it says, I want to be with you, I don't want to be with you, I don't want to be with you, she didn't want to be with him. So basically you can see that as you interpolate between these, they get to be similar. He was silent for a long moment, similar things like this. So this is kind of a trivial example, but you can also think of less trivial examples where you would actually want to use these vectors as a way of measuring semantic similarity or something like this. And in that case, you really do kind of care that the space is consistent and that things that are close to each other are actual real sentences that are similar semantically. And we actually had some work on training multilingual semantic similarity models where we added a VAE objective, and that improved the correlation with semantic similarity as well. Another thing is they might be more robust to noise. So VAE can be viewed as a standard model with some regularization on top. And because it's a standard model with regularization, it may be less likely to fit the spurious correlations. It also has a sampling operation included within it. So that means that a small perturbation of the representations is less likely to make a big difference in the output because during training you're doing the sampling. So standard VAEs were used for a long time on image generation and other things like this. But there are some difficulties in training models that are particularly bad for natural language. And it's not just natural language, it's any kind of sequential data in general, but natural language is one example of that. And one problem is that of the two components in the VAE objective, there's two terms, if you remember, the reconstruction term and the KL divergence term. And the KL divergence term is much easier to learn. So if we look at these two components, in order to learn this requires a good generative model. You need a good language model. you need a good image generation model or something like this. However, there's a trivial solution for this KL divergence term, right? You just set the mean to 0 and the variance to 1, covariance to 1, and you have a perfect approximation of this term. So what tends to happen is early in model learning, the variational autoencoder learns to rely solely on the decoder and ignore the latent variables. So basically it learns the inference network to just predict the mean, the prior every single time. And so because of this, because this latent variable becomes completely uninformative, this generative model also becomes completely uninformative and just predicts based on the language model every time. So there's kind of a chicken and egg problem where you need a good latent representation to learn a good latent conditioned generative distribution. And you need a good, but that's hard to learn because this is so much easier to optimize than the thing on the left. So there's a few solutions to this. One is called KL divergence annealing. And this was introduced in the original Bowman paper that applied this to natural language. And the basic idea is to multiply the KL term by a constant, starting at 0 and then gradually increasing to 1. So basically what you do is you start out learning an autoencoder, a regular autoencoder, and then you gradually turn it into a variational autoencoder, essentially. And as a result, the model can learn to use Z before getting penalized with the KL divergence term. And you can see that as you gradually, before you increase the KL divergence weight, you get a big KL value. And then as you increase the weight, it decreases, but it doesn't decrease all the way to 0. So it's not collapsing completely. Another idea is something called free bits. And free bits basically replaces the KL divergence term in elbow with a hinge loss that maxes each component of the original KL with a constant. And so basically what this is saying, this is called free bits because it's giving you a few like free bits of information that you're allowed to use to predict the latent variable with the inference network. And so this is a this isn't actually directly maximizing the elbow anymore. So if you wanted to turn this into a real autoencoder, you'd also have to take this lambda term and gradually decrease it to 0 until you actually got the KL. So another solution is to do something like weaken the decoder model. And so we can so one even the two previous solutions that I talked about before are still theoretically problematic. It can be shown that when you don't need Z or when Z doesn't provide additional information compared to the original input, you can basically like ignore Z when it's not useful. And so if you have a very strong decoder, like let's say you had a really, really strong language model on your output side, much of the time Z would not be helpful in predicting the output or not give like only a very marginal improvement. And so one solution is to weaken the decoder so that using Z is essential in order to get good accuracy. So one example of this is to use word dropout to occasionally skip inputting the previous word in X. So basically, if you have an autoregressive decoder that conditions the output based on the input, you can occasionally drop out the previous words, and that makes it harder and thus more useful to pay attention to Z. And another example is work that uses an intentionally weaker decoder so that you learn better latent representation. So they used a convolutional decoder with limited context, so you could only look at the few previous words. And because of that, in order to get like a global view of the sentence, you would still need to use this, this Z here. So these are just two examples of this. A final example is aggressive inference network learning. And so basically, if we have the data log likelihood and the agreement or the KL term, so basically the likelihood of the KL term, normally we optimize these jointly. So like every update of the model, we optimize both the inference network and the model, the generative model itself. But the idea here is that we set up the model. So basically we aggressively optimize the inference network first, and then take a step to optimize the model. Aggressively optimize the inference network first, take a step to update the model. And so the idea here is that this allows the harder, this allows basically the inference network to learn good latent variables that are useful to the generative model. By like changing the optimization dynamics, it helps prevent this chicken and egg problem. Like the inference network is always producing useful steps, so the generative model doesn't learn to ignore it. Cool. So this is the standard variational autoencoder where we have a latent continuous vector that you're optimizing things over. Are there any questions about that before I get into handling discrete latent variables? Yeah. Yeah, so I went over that very briefly before, and sorry, I noticed that as I was explaining the slide, but I was hoping that nobody would get confused. But basically, these two things are kind of related. So if you look, here and take this on this, like move the KL over here, then that's equivalent to the equation that I just showed you. So it's kind of basically an alternative way of displaying the equations here. I would definitely suggest looking at the tutorial materials that I have up there. I can't recommend them more highly. So once you do that, I think it should be clear the relationship between all of those. But basically, it's equivalent. It's not a it's just a different way of writing the equations. Great. Any other questions? Okay. So all of the stuff I talked about so far has been, slightly flavored with NLP, but, also largely could be used for other things like image processing or things like this. I think the next part is the thing that's really interesting within NLP, and it also has a lot of potential for like creativity in the use cases. So handling discrete latent variables. So what are discrete latent variables? Many variables are better treated as discrete, like the part of speech of a word, the class of a question, for example, writer traits, whether a person is left-handed or right-handed when you're modeling their writing style or handwriting or something like this. And so how would we handle these in a variational autoencoder? And if you remember, the problem in the variational autoencoder was that we had an integral that was intractable. But when our space over latent variables is discrete, when we only have like left-handed or right-handed, for example, we have two choices. The person is either left-handed or they're right-handed. And because of that, we could just theoretically calculate this integral completely, like by enumerating over all of the possible values of the discrete variable and calculating the probability of both. So that actually would make our life easier in cases where we can do this. We just directly calculate this marginal likelihood and we're fine. However, most cases, this is not the case. If we have interesting discrete latent variables, maybe we have a finite number of them, but the finite number is very large. Like, let's say we have 100 classes, and the 100 classes, 100 topics that we could be sampling over, it would be too much to calculate 100 different language model probabilities over sentences for all of those classes. If we have something like our latent variable is a sentence, then obviously that's completely impossible because the number of sentences is combinatorially large. So method number 2 is sampling. So what we do is we can sample a subset of the configurations of Z and optimize with respect to the subset. We talked about some very simple examples of this last time, right? You know, we sample using minimum risk training to maximize the elbow loss. We could also have a policy gradient method like the reinforcement learning methods that we talked about before. So basically what we would do is we would have an inference network or something like this over the various values. We would sample 1 or 5 or 10 values. We would calculate the generative probability of all of them, and then we would update the inference network using reinforce. So that's another option that we can use. So because this is basically the same as what we talked about last time, I'm not going to talk about it in a lot of detail. The kind of more interesting thing is that there's not exact reparameterization tricks for discrete variables, but there's something that's like the reparameterization trick for discrete variables that's kind of close enough to make it useful. And so if we think about the original way we could sample a categorical variable, what we do is we calculate the probability distribution over the variables, and then we sample a one-hot vector. So we might have our P of Z might look like 0.5, 0.3, 0.2. And then the categorical sampling, what the categorical sampling function would do is it would give us this one hot vector 0.5% of the time, this one hot vector 0.3% of the time, and this one hot vector 0.2% of the time. And so this is the normal sampling method. This is non-differentiable because we can't calculate gradients through this. However, we can do reparameterization. And the way the reparameterization works is we now have an argmax where we take the log probabilities here, and then we have a Gumbel noise here. So Gumbel noise is basically, if I remember correctly, you sample from the uniform distribution, and then you take the negative log of the negative log, or something like that. That's basically the distribution here, and you can actually show that these two things induce the equivalent distribution. They give you the same thing over here, like this. And so this is good in a way because basically we no longer have this cat sample thing, which is completely undifferentiable. We have a log probability, which is differentiable, and then this Gumbel noise, which is non-differentiable. However, we still have a problem, which is this argmax, and the argmax function is also non-differentiable. Oh yeah, there's the Gumbel distribution. But backprop is still not possible here due to the argmax being non-differentiable. So what we can do instead is something called the Gumbel softmax. And the Gumbel softmax is a way to soften the decision and allow for continuous gradients. So instead of the argmax, we take the softmax with a temperature T. So we do the normal Gumbel noise here. We exponentiate it by 1 divided by tau, sorry, not T, tau. And then we take the softmax over this. And as tau approaches 0, this approaches the max. So this is a figure from the original paper on this. And the categorical distribution looks like this. This is our expectation here, and we have a single sample. It gives us a 1 hot. If we set this tau to 0.001, we'd basically get something that looks indistinguishable from the categorical distribution. However, if we set tau to be very large, we get something that looks very flat like this. And also the gradient flow through this distribution, or this distribution, will be much better than the gradient flow through this distribution. We'll have very peaky gradients for this distribution over here. But for over here, we'll have some gradient flowing into each of these values. So one thing you can do with this is you could like set the temperature to be equal to 1 all the time and do the sampling, or you could set the temperature to start out at a high value and gradually anneal it down to a very low value. So you start moving towards something that looks like the actual sampling that you would be doing in training the model. So this is kind of the discrete version of the clever reparameterization trick, but unfortunately, as with everything else discrete, we still can't do things like argmax to learn this example. Are there any questions about this? Okay. This paper is written relatively well as well, so you can go back and take a look at it. Yeah. Okay, so I'd like to go with a couple examples of applications in NLP of learning latent variables. So one common example of this, one actually quite common example of this compared to most of the other examples I'm going to talk about, is learning latent variables that are sequences of symbols or more precisely text. So the latent variable itself is text. In fact, this paper is called Language as a Latent Variable. And what you do is you have the encoder decoder with a sequence of latent symbols. And so you have the encoder that tries to output a sequence of latent symbols. And then you have a decoder that tries to reconstruct the input. And this was done for summarization, for example. And the way summarization works, the way this works for summarization is basically you train a model. You ask it to compress the sentence down into a shorter sentence, and then you ask it to generate a longer sentence. And so this could be used for like fully unsupervised summarization, for example. You could just try to get the model to compress to a shorter sentence and then output a longer sentence. So as a quiz here, what would you use for a prior in a model like that? What would be the prior probability over your latent variable? Yeah. Would it be Gaussian? So here the latent variable is text. Sorry, actually this is very abstract, so it's hard to tell. So the latent variable, you'd also want it to be text. And ideally, you would want it to be a good summary of the original input. So any other ideas? Yeah. Distribution of the original input, that's close enough that I'll call it correct, but you could just train a language model because you know you want the input in the middle to be a summary that looks like good text. So you could train just a language model, and that would be your prior over what the input in the middle looks like. There's also examples of where you can use this to discover language. So basically, you might have an input which was an image, and then the encoder and the decoder are handling images, and then the thing in the middle is a discrete sequence of symbols. So the idea is that you want to encode the image into a sequence of symbols like 32, 45, 15, and then output the image here. So this is another example, and this is called emergent communication in the literature. And basically, the idea is that you're trying to find like agents that are speaking with each other are trying to like discover a language with which they can speak to each other. I think this is kind of interesting with the one caveat that in reality, almost never language almost never actually emerges that way. Usually you learn it from your parents and your parents teach you how to learn it, but there are some cases where Luke Steele's. Yeah, I actually don't know. Yeah, it might be. This kind of stuff. Yeah, yeah. I am not familiar with this work, but it'd be fun to look up. There's two other examples that I realized I forgot to put on here. So one really nice example that's used very widely, partly in most widely used in speech, is something called the vector quantization VAE. And this is basically a discrete VAE, but they have a kind of tricky way of learning it. I think this is the best example here. And basically the way they learn it is they learn it by having nearest neighbor prototypes. And you basically look up the nearest neighbor in this embedding space and use that as a way to decide which discrete representation you're learning. So it's a little bit different than like predicting according to a probability distribution. Rather, you're taking the nearest neighbor or several nearest neighbors in order to discover the latent representation. Another example is one of my papers. So sorry, you're in this class, so I get to talk about my stuff sometimes. But nonetheless, I think this is another interesting example where basically here the latent variable is the same text, but in a different style. So like, for example, you could have the input text is in informal style, the output text is in formal style. You don't have any paired examples because nobody goes around like translating between formal style or informal style, or it's not super common to do that. But you do have lots of examples of formal speech and lots of examples of informal speech. So here, the language model over the latent variable is a language model of like informal speech, but your input to the autoencoder is the language model for formal speech, for example. So this is another example of how you could formulate that in the VAE fashion. There's a couple other nice tricks in the paper how to train the models as well. Like we pre-train the decoder and the encoder and other things like that. So you might want to take a look. So another example of a VAE style model that has been used to induce latent variables is inducing latent tree structure. So this is a little bit similar. Actually, I forget if Howe talked about the recurrent neural network grammars. Did he? I think maybe not. Yeah, nobody's saying yes, so I'll assume no. So basically, a recurrent neural network grammar is basically a kind of, it's like a shift reduce parser, but it's a generative version of a parser that uses tree structure. And originally they were trained in a supervised manner, but this basically is a VAE style formulation of this where the latent variable is a tree, and then the tree is used in the generation of the output. So this can induce essentially a tree structure over text by learning this latent variable kind of in an appropriate way. This is another example from one of my works. This uses a semi-supervised formulation where we have a small amount of supervised data, which allows us to learn the inference network in a supervised fashion. And then on a whole lot of unsupervised data, you can then run VAE style inference to try to learn latent tree structure. So the idea that we're learning tree structure is the same, but in this case, we used it over like semantic parsers instead of syntactic parsers. So this would be useful, like we talked about semantic parsers as ways to do question answering or something like this, right? So that would be useful if you had a very small corpus of annotated data that you could get from annotators, but a very large corpus of query logs or something like that you would want to be training a model like this on. And in terms of your prior, you could even think of things like whether the underlying logical form executed to give you a appropriate looking answer for the question or other things like that. So there's lots of space where you could get creative and something. Cool. So yeah, that's all I have for today. The methods that I presented here are a little bit more complicated than a lot of the methods that people would be using in like a production system or something. But at the same time, I think there's a lot of room for creativity in how you can use them, so they can allow you to do things that you might not be able to do otherwise, which is why I think it's worth spending a class on them. Any final questions? Yeah. Yeah. So basically, because you have the gumble in here, this is sampling essentially. So it's a reformulation of sampling, but because every time you have gumble noise, every time you'll get a different distribution there, essentially. Yeah. Yes. Yeah, so this is a very good question. So compared to GANs, which I'm going to be talking about next time, generative adversarial networks, VAEs tend to generate images that are like fuzzier, or like they don't look as sharp as the things that GANs generate often. And I think that actually kind of makes sense. And the reason why I think it kind of makes sense is the VAE has to model the distribution of all images. It has to give probability to essentially all images well. Whereas for a GAN, it basically has to just generate images that are high fidelity enough to fool a discriminator. It doesn't have to model the whole space of all possible images. And because of this, the GAN is free to generate more, the GAN is free to generate more high resolution images, but it's also like, it might have images with less diversity or other things like this. So it has other problems. It also, I'm gonna have a explanation of this later, but it also isn't easy to calculate a good probability distribution based on it. I imagine the problem is similar for text, which is that text generated by GANs would probably, there would be fewer easy giveaways that it was unnatural text, but at the same time, it wouldn't necessarily be as diverse, or it might not be able to cover the long tail of all of the sentences that somebody could be generating. But I actually, I don't know of any. So number one, GANs aren't actually used that often to generate text in the first place. And part of the reason why is because GANs are hard to optimize. And anything that's hard to optimize for images is going to be even more hard to optimize over text. I think because of that, there's not really a good comparison between like if you used a GAN versus if you used a VAE for text. And there's maybe not even a like extremely good comparison of if you used a VAE versus if you used a regular language model for text either. So sorry for kind of rambling long response, and the like summary is that's a good question, but I don't really know the answer. I only have some conjecture like what I just said. Any other questions? Yeah. Yeah, really good question. So how do we, when we're doing like text style transfer, what do we do at the time of generation? And there's actually two questions here. So when you're doing text style transfer, actually the way you do it for text style transfer is the style transfer method. The style transfer method uses the inference network. So you take in the input and you generate the you just generate the latent variable, and that's all you do for style transfer. So in other words, you would take in an informal sentence and generate a formal sentence if the formal sentence was a latent variable. If you are doing generation, if you want to treat it as a generative model, what you would do is you would sample a sentence from your formal language model. You would have your pre-trained like formal language model that was trained on lots of formal sentences. You would generate a sentence from that, and then you would use the generator model to generate the corresponding informal sentence. So it's basically like a style transfer is Q of Z given X. And then generation would be, you generate P of Z and then P of X. Did that answer the question? Cool. Anything else before we wrap up? Okay, thanks a lot, everyone.